Welcome back, everybody. Today we're going to be talking through our Test 2 review and trying to get some perspective on it. In this video, we're not going to be kind of working through any of the details of the problems, but the idea for today is to try and get some sort of higher perspective on these problems. I feel like maybe at this point we've been kind of hacking our way through the trees with a whole bunch of different problems and power series and functions and stuff like that. And what today is about, this video, is about trying to kind of come up from that and get some higher perspective on the landscape. We're just going to take some time and talk about what stands out to me with each of these problems and the basic ideas that are involved and the basic plan for going through and doing what we need to do for each of them. Right? And so let's just start on in. The top here, this is us just thinking about series, a regular old series, right? Before we had any variables involved. Remember those days? And so to start, I want to take a minute and kind of think about these questions that we had figured out are helpful questions to ask when trying to kind of get a feel for what might be a useful way to analyze the series and test it for divergence or convergence. And so we did this with our group work with section 11.7. So if you have that, take a second and grab that group work. It's up near the top, the questions. Even if you don't have it, I have it up here, and so let's switch over there. Here's our group work and the different questions. This is a nice order to think about these in, right? The first question that's super helpful to ask is, are our terms going to zero or not, right? And this is just a shorthand way of asking, hey, does the limit as n goes to infinity of our terms an actually equal 0 or not, right? And if not, if our terms don't go to 0, then test for divergence tells us what's going to happen, right? But if they do go to 0, we don't know what's happening. We need to do some more work. All right, so that's kind of the first question to start with. Next, is the series something that we actually just know about? Is it literally just a geometric series or a p-series? And recall the idea with both of these. Right, geometric series, those are series that look like sum from n equals 1 to infinity of a r to the n minus 1, right, where we have some starting term and then our following terms just come from multiplying by r, and that's a geometric series. And our p-series, and those are series that look like just 1 over n to some power. I think we started those at 1 over n to some power. All right, so if it's literally one of these, well, then we know what's going on. All right, we have our check for the geometric series that depends on the absolute value of the r, and the check for the p-series that depends on the value of the power there, p. The next question is, can we see the basic structure of an when n is big? Right? The idea is, does my function somehow kind of collect or simplify in a nice way if n is really big? Are there things that matter more? And if so, well, then the limit comparison test might be a good way to go. Our direct comparison test, I would say to shy away from in general, unless we're using it as part of a absolute convergence test. All right, the direct comparison test, we need to be real careful about how our function changes, whether we're getting bigger or smaller with each piece that we're getting rid of. And at the end of the day, right, if you get a comparison series that's bigger and that thing diverges, well, then you don't know anything, right? It's the wrong direction. And so it can kind of fail in two ways. And so limit comparison test is a more versatile test that I think we should focus on. Our next question is my series alternating, right? And the idea there is, right, do we just have essentially like some -1 to the n or n plus 1 or something like that, right, going on, and then we have, some other non-alternating stuff after that. And if so, well, alternating series test, probably a good way to go. If it's not alternating, but we still have some positive, some negative stuff, that's when we can bring out the absolute convergence test, right? And the idea here was to look at the series where we take the absolute value of our terms, and we'll try and show that that thing converges. Right? If this converges, then we've done the harder thing, and our original series will converge as well. Right? And oftentimes, once we've slapped the absolute value on this, we want to use the direct comparison test to find like a bigger series. And then once we have that bigger series, we can just use whatever other test might be appropriate for thinking about what we're staring at then. Afterwards, some other questions. Are there any factorials or some exponential stuff? If so, in the ratio test is probably going to be helpful, right? And we do also have the root test. It doesn't show up as much, but that's useful if our terms are just essentially something to the nth power. If they are, then our root test will allow us to kind of cancel off that nth power, and taking the limit will allow us to hopefully make a conclusion. And I have last on the list our integral test question, just because it takes normally a substantial amount of work to check all the hypotheses and then compute the improper integral. But there, the question is, can I integrate an, right? Or in other words, if this was an integral instead of a series, could I do it? And if so, well, then the integral test might be a good way to go. All right, so those are our basic questions. That's kind of our what we're looking for as we're trying to kind of feel out what's going on with this series. And so with these in mind, let's come back to our list over here in our review and kind of talk through what we might notice about these. Oops. All right. So for our first series here, let's just start at the top and ask the question, I'll write it out real formal. Oops. Does the limit as n goes to infinity of our terms equals 0, right? And again here, an, those are just the things that we're adding up. There's our an. And let me just say, that's going to be a useful question to think about for this one. All right. For our second series down here, what sticks out to me immediately is that we have this alternation term, right? It's -1 to the n, and the stuff over here to the right, that's not alternating. And so this definitely suggests using the alternating series test. And I think that that'll be able to get us there. And for our next one, here we're looking at this series. And what immediately stands out to me for this one is the factorial. Right, factorials in general just cry out to use the ratio test. And we even have an exponential bit up top, ratio test. It's going to be helpful. And maybe just as we're going, why don't I just remind us about the basics of these tests, what they ask us to do. Right, with the ratio test, we want to look at the limit as n goes to infinity of the absolute value of our ratio of successive terms. All right, we'll do a bunch of work, compute that, and we'll, whatever that is, that's our L. And right, the idea is that if this L is less than 1, then our series converges. If it's greater than 1, our series diverges. If it equals 1, then we don't know. That's the basic idea there. And yeah, since we're talking about this, for alternating series test, right, we'd want to take a look at our non-alternating bit, our Bn. And the first thing we want to check is Bn decreasing? And then we want to check to see if our Bn terms are going to 0. And if those are both checks, that says if, then our series converges. All right. If not, we can probably make use of another test to make a conclusion about our series. All right, moving on to number 4. I'm looking at this one. If we just want to maybe walk through the questions here, right? Do the terms go to 0? Well, yeah, it looks like it. Our numerator is what's blowing up. Our numerator is constant. Our denominator is blowing up, so the terms are going to go to 0. It's not a known series. Nothing really seems like it's going to kind of disappear if n is really big. There's no alternation or anything going on. This thing's all going to be positive. There's no factorials. There's a little bit of exponential stuff. There's a natural log in there, which is going to make the ratio test super weird if we try and work that out. Thinking about the integral test is the one that's kind of left at the bottom. And here, you know, if this series was an integral, I claim that we could make this work. And so this is, like, if we just look at the terms here, it's something we could integrate. And so with this one, number 4, our idea is to use the integral test, right? And right, for that, we'd want to, you know, check continuous, positive, decreasing. All right, and here, continuous and positive, we can just check those in our heads. If this thing is decreasing, might have some work to do there, but actually for this one, I'll just talk through it. For our terms here, our numerator is just constant. And so here to check decreasing, it's literally enough just to say this is 1 over something that's increasing. And so that's our check for decreasing here, right? And so then we just need to compute our integral from, I guess, 2 to infinity of right, this thing where we replace the n's with the x's. And let me just write whatever that thing does, our series behaves the same. Right? If this integral diverges, that's what our series does. If this integral converges, that's what our series does. And again, we know that our series behaves the same because our series here passes these three checks, these three hypotheses. So integral test is going to be a way to work through that one. All right, so number 5, looking at this one, if we wanted to start from the top of our questions, do our terms go to 0? Well, here our power of n in the bottom is bigger than the one up top, and so we'd be able to show with L'Hopital's rule or something like that, yeah, these terms are going to go to 0. The denominator is going to be more powerful. Is this a geometric series or a p-series? No, it's not literally one of those. Is this thing going to kind of collect or simplify nicely when n is big? And there, I think yes. What stands out to me right away, this is a rational function, and when n is really big, we're going to lose all the terms that aren't as powerful as the most powerful one, right? So there's nothing really going on up top, but when n is really big, this -3 won't matter too much, and our series, let me just kind of do a little thought bubble over here. When n is big, this thing should more or less look like the series for 2n squared over 5n to the 5th. And if we just forget about the constant multiple of 2 and 5 there, n squared over n to the 5th, that's going to be 1 over n cubed. And that's a series that we know about. In order to kind of connect that to this series that we're starting with, right, this series we know about is not equal to this series, but right, this idea that, oh, when n is big, it should look like this, right? This is telling us, oh, let's use the LCT. Let's make use of that and compare with bn being the 1 over n cubed, right? Or you could do 2 over 5n cubed if you wanted to keep the 2 up top and the 5 in the bottom around. That would work as well. With this one, if you were thinking direct comparison test, well, let's think through what would happen there. So if we'd want to think about getting rid of the -3, we'd want to add 3 to the numerator, which would make the denominator bigger, which would make the fraction smaller. And I think the series that we'd be left with would converge, and so our smaller series would converge, which wouldn't tell us anything about our bigger one here. And so, just as a quick summary, direct comparison test fails here, right? But limit comparison test is going to be able to get us there and allow us to conclude. All right, our last one on the list here looks horrible, right? Sine of n to the 2019. Those were the days. Those were the days. And so it looks horrible, but I think maybe what makes it horrible is something that really stands out to me is the sign of this weird thing, right? And what stands out to me is sine is a function that as it takes inputs is going to be positive and negative, but it's not strictly alternating. It's not going to be positive, negative, like our alternating series was up here. It's going to be positive and negative, but not alternating. And because of that, our absolute convergence test is going to be a useful way to think about this, right? Absolute convergence test says, well, hey, let's look at the series for the absolute value of, let me just do it like the sine of that over 2 times 5 to the n, right? And here the observation, right, is that since sine is bounded between -1 and 1, oops, I'm sorry, since sine is bounded between -1 and 1, sine of whatever is still going to be bounded between -1 and 1, and so the absolute value of that, right, at most is going to be 1. And so here we can make use of that and get a bigger series here where we replace the sine with that value of 1. And then on the bottom, right, that's always positive, and so we can leave that alone. All right, and so this is our bigger series. And this is the series that we now kind of just need to go through our questions again and try and figure out how to test, right? And the idea is, you know, if this thing converges, then our smaller series converges by our direct comparison test. And then if it's true that our series for the absolute values of this stuff converges, well then by the absolute convergence test, then our original series converges. So we have this kind of two-step walk down. We just need to kind of figure out whether this thing converges or not, and we'll have a certain test that we'll need to, you know, to make that conclusion. But that's how we can kind of walk back there. All right, so those are our series we're testing out. Let's move on. All right, variables, right? Looking at power series are infinite polynomials. And so for this first one, find the radius of convergence and interval of convergence of this power series. And so what stands out to me, first of all, what comes into my mind is the radius of convergence. To do that, we'll want to use the ratio test. And that's what we'll use to figure out which of our kind of 3 possibilities this thing's in, right? And those 3 possibilities are that this thing converges only at its center, which pop quiz, what is the center of this power series? Remember, we can spot the center by seeing what we have. I get to the x minus a to the n, right? And that's how we can spot our center. Here we have x plus 1, which we can think of as x minus -1, right? And so here our center would be -1. So this thing's either going to only converge there, or it's going to converge on some, you know, finite interval or symmetric interval around -1, or it's just going to converge everywhere. All right, those are our 3 possibilities from our radius of convergence test. All right, and so the ratio test will allow us to figure out which one of those that we're in, will allow us to find the radius of convergence. And if we are in the second case, then we have a little bit more work to do, right? Because these kind of boundaries, that's where the L from the ratio test equals 1. And so we would, if we were in the second case, need to check those in order to find the full interval of convergence, right? Because the interval of convergence, right, that really is just our fancy word for the domain of our power series, the full domain. All right, looking at B, we're wanting to use known series to evaluate the integral. Write your answer in standard form. What is the radius of convergence? And so what stands out to me, first of all, is that we're asked to use a known series here. So we have our 6 functions that we know how to write as a power series. And so looking at the function that we can see here, which one of those are we going to be able to make use of? It's actually going to be our very first one. Right, the 1 over 1 minus something, right, which with maybe some stuff out front. And so here, since we're trying to evaluate the integral, we kind of have 2 steps. First step is to make this thing kind of look like this, so that we can write this as a power series. Let me say then, write as a power series. Once we write it as a power series, we'll maybe need to do some work to get this power series that we are able to swap this out with into standard form. But once we have it in standard form, we'll be able to do the second step, which is to integrate. All right, so integrate our power series. And again here, I want to get this into standard form instead of like expanded form, just because we're asked to do the standard form for this one. For the radius of convergence, let me just say that in general, how we do this is we use the ratio test, right? Like we would do up here in this part A. That's in general, but I claim that when we can relate our function to this form, right? This is the form that we get for our geometric power series. We have a much faster way, much cleaner way to get at the radius of convergence, right? And the idea here is that this thing equals its power series when, right? What's the check for our geometric, right? It's when the absolute value of our r is less than 1. Well, here it's the absolute value of the box is less than 1. And so let me just say, when we're looking at the radius of convergence, we can find it using this inequality, again, when our function, we're using this formula, right, for our geometric one. So if we're using this formula, then we have a quick way of grabbing that. In general, right, if we were just up here, wondering what this thing's radius of convergence is, we could use the ratio test. And if we did, the ratio test correctly, we'd get the same thing for our functions power series here. This is just going to be a much, much cleaner way. All right. Next one, I use the definition of Taylor series. And so right away, what stands out to me is we're going to be taking derivatives, lots of derivatives, right? And to find a power series representation for this function centered at a equals 2, you may leave your answer as an expanded sum, so we don't need to worry about getting our power series into summation notation, finding the general pattern and all that. And it just wants the first 4 non-zero terms, right? And with a plus dot 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 because it's an infinite polynomial, right? And so yeah, so the idea here, right? Definition of Taylor series, right? We know that our power series representation looks like this, right? Our nth derivative evaluated our center over n factorial times x minus a to the n. Right, that's our kind of standard form summation notation version of this thing. Right, and how that looks written out, right, is our first term is f of a, then, sorry, I guess our n equals 0 term is f of a, n equals 1 term, it is first derivative evaluated at our center times x minus a, and then our next term is, right, the second derivative evaluated at our center at over 2 factorial times x minus a squared, similarly, moving on. Right, and so whenever we're wanting to use the definition of a Taylor series, we're going to be computing derivatives. All right, we're going to want to start with, what is our f of x, and then our f prime of x, and our double prime of x, right, f triple prime, etc. And then we'll want to see what we get when we plug in our center to all of these things. Oops, still on the eraser. F double prime of a equals something, right? And if we were wanting to get our power series in standard form, well then we would want to figure out the pattern here, for our, hey, what's the nth derivative of our function evaluated at the center going to be? But actually, since we're just wanting the expanded sum, we don't need that. We can just crank out enough derivatives to get 4 non-zero terms and put them where they go in the formula. All right, moving on, got some true false. All right, for this first one, if the limit of an equals 0, then the limit of an converges, then the series for an converges. Is that true or false? Let me just say, think about what the test for divergence says and what the test for divergence does not say. I'll write that down since I'm writing notes. Think about test for divergence. For the second one, if the partial sums of a series have a limit, the limit of the partial sums as n goes to infinity is 3/2, then the series converges. For that one, I would say think about the original actual definition of convergence or divergence for series. This was way back at the very start of 11.2. For this third one, If a series does not satisfy the hypotheses of the integral test, we can conclude that the series diverges. Again, here, I encourage you to think about what the integral test says and what it does not say. All right, that's it for today. Hopefully this was helpful in trying to get some higher perspective on the ideas that we've been working with. That's it for today, and I'll see you next time.